What's up, algebros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Today's a very special day. We're going to be taking a look at the inverse of a matrix. And we would say that if we have a matrix A, the inverse of that matrix A is A inverse, denoted as follows, A inverse. So let's talk about A inverse today. So A inverse is the inverse of matrix A. Couple properties. A inverse times A gives us the identity matrix. Or if I want to multiply it in the other direction, A times A inverse gives us the identity matrix. So we get some nice properties with the inverse. And we're going to start by talking a bit about 2 by 2 inverses. So let A be a 2 by 2 matrix with a first row with entries A, B, a second row with entries C, D. Then A inverse has the following closed form. It's 1 divided by A times D minus B times C. Think of this like a coefficient. And we multiply that into the following rearrangement of our original matrix. So the entries on the main diagonal from upper left to bottom right, we swap those. So instead of A and D, we have D in the upper left and A in the bottom right. And then the entries on what we call the off diagonal, we keep those where they are, but we flip their sign. So instead of B, we have negative B. Instead of C, we have negative C. And this is how we find the inverse, unless there could be a problem, right? What if A times D minus B times C is 0? Then I have this coefficient of 1 over 0, which, that's not going to do us any favors. We would say A is not invertible in that case. And actually, this denominator, this A times D minus B times C, is the determinant of that matrix A. So that's actually the determinant of a 2 by 2 matrix. We're going to talk about determinants later on in the course. So right now we just sort of briefly mention it in passing, but we will be talking about determinants later on. We have a nice theorem. If A is an invertible n by n matrix, and to find an inverse, we need a square matrix. There are such things as sort of pseudo-inverses, a left inverse and a right inverse. We're not talking about those. That's not what we're going to be talking about. We're talking about a true inverse. To have an invertible matrix, we need that it's a square matrix. So if A is an invertible n by n matrix, then for each B in Rn, the equation Ax equals B has the unique solution x is equal to A inverse times B. And let's actually show this. Let's see if we can get some idea as to how a proof would look. So first, we can see that x equals A inverse B is a solution, since A times x is equal to A times, and here x is A inverse B. I make that substitution. And here I can regroup. I can say, well, this is the same as A inverse times B. And A times A inverse gives me the identity times B. And the identity times B gives me B. So this is a solution. It does satisfy Ax equals B. So we know that x equals A inverse B is a solution. Now to see that it is unique, let's assume there is another solution, u, to Ax equals B, where u is not this A inverse B. So we're saying, okay, let's see if it's unique. Let's do this by contradiction. Let's assume there is some other solution, and it's not the same thing. Let's see if this can happen. Well, if A times u is equal to B, so then A times u is equal to B, we're saying this is a solution. Let's see if we can solve for u. What I can do is I can multiply by A inverse on the left of each side. And then here I can regroup and say, well, so think of this like A inverse times AU and then equals A inverse times B. If I regroup this, A inverse A times U equals A inverse B. A inverse times A gives me the identity times U equals A inverse B, which then the identity times U gives me U is equal to A inverse B. And this is a contradiction. We said, well, U is another solution, and it's not A inverse B. But we went ahead with it, and we showed that it is this A inverse B. It's the same thing, so it's not different. It's not a different solution. So then we can conclude here. So then the solution is unique. So we do have this unique solution. Take a look at a couple theorems. We got a theorem: if A is an invertible matrix, then A inverse, its inverse is also an invertible matrix. And if I invert twice, A inverse inverse brings me back to A. So if A is invertible, then the inverse is also invertible, and A inverse inverse is equal to A. If A and B are n by n invertible matrices, then the product A times B is also invertible, and the inverse of A times B is the product of the inverses of A and B in reverse order. That is, AB quantity inverse is the same as B inverse times A inverse. And that might even sort of remind you a bit of what we talked about with transposes, a similar property for transposes. And we have, if A is an invertible matrix, then so is A transpose. So there's actually a typo here. I'll fix it right now in real time. If A is an invertible matrix, then so is A transpose, and the inverse of A transpose is the transpose of A. I think so. Well, let's see what this is saying. This is saying A transpose's inverse is A inverse transpose. So the inverse of A transpose is the transpose of A inverse. Okay. So let's see what we're saying here. I think I got all the things fixed. I'll fill in the rest. If A is an invertible matrix, then A inverse is an invertible matrix. So then A transpose is also invertible, and the inverse of A transpose is the transpose of A inverse. So I think that's what we're trying to say here, that A transpose, its inverse, is the same as A inverse's transpose. So a nice property there. The product of n by n invertible matrices is invertible, and the inverse is the product of their inverses in reverse order. And this is what we said here for this second statement. Just want to have an extra disclaimer there. And another theorem, an n by n matrix A is invertible if and only if A is row equivalent to the identity matrix. And in this case, any sequence of elementary row operations that reduces A to the identity also transforms the identity into A inverse. And we're actually going to use this theorem together today, and I'll show you how we can use it. Now let's take a look at some examples. Find the inverse of the following matrix. Now let me just refresh. We said A is a 2 by 2 matrix with a first row AB, second row CD. A inverse is 1 over the determinant, which is A times D, multiply on the main diagonal, minus B times C, multiply on the off diagonal, subtract. And that scales into the following rearrangement. On the main diagonal, upper left to bottom right, we swap those two. So D upper left, A bottom right. Off the main diagonal, we flip the signs. So B stays, but we flip the sign. C stays, but we flip the sign. And that's our formula for finding a 2 by 2 inverse. Let's go ahead and do it here. So A inverse, I want 1 divided by, we multiply on the main diagonal. So that's 2 times negative 6. And then I want to subtract the product on the off diagonal. So then minus, and then it should be negative 4 times 4. And this is going to scale into the following rearrangement of our matrix. On the main diagonal, we swap those entries. So negative 6 in the upper left, 2 in the bottom right. Those other entries, we're going to flip their sign. So negative 4 is going to stay where it is, but I'm going to change its sign to positive 4. Positive 4 is going to stay where it is, but I'm going to flip the sign to negative 4. Now, I'm not quite done with this. I want to actually solve for this inverse, but we just got a little bit of work left. So this is 1 over, here I have negative 12, and this is going to be plus 16. I got that double minus sign. And let's go ahead and find this coefficient. 16 minus 12 is 4, so that's 1/4. -6, 4, -4, 2. And then if I bring this in, I can divide, or where it doesn't divide cleanly, I can reduce. So let's bring in that 1/4. -6 divided by 4 reduces to -3/2. 4 divided by 4 gives me 1. -4 divided by 4 gives me -1. 2 divided by 4 gives me 1/2. So this is A inverse. We have an interesting follow-up question. Solve the system. Here we have 2x1 minus 4x2 equals 2, 4x1 minus 6x2 equals 10. This is really, if I convert this into a matrix equation, and let me actually write out that matrix equation, I get a coefficient matrix. Take the coefficients, 2, -4, 4, -6, times this vector x with entries x1 and x2 equals this vector which we usually call b with entries 2 and 10. So this is really just another way of thinking ax equals b. But what do you notice about matrix A here? That's 2 minus 4, 4 minus 6. That is the same matrix that we just found the inverse to. And if you remember from the very beginning, we said since A is invertible, there should be a unique solution. So the solution is x equals A inverse times B. Now, I can solve the system like we've been doing already. I can row reduce and stuff like that. But the idea in the section is now I can use the inverse that I just found. So I can say, well, what is A inverse? I just found A inverse. It was -3/2 1 for this top row, and then -1 1/2 for the second row. So there's A inverse. And then times B. B is this vector with entries 2, 10. And if I just compute this directly, it's going to give me the solution for x. Well, so let's do it. So here I can use my row vector rule, -3/2 times 2. So here the 2's cancel, so I get -3, plus 1 times 10 gives me 10. That's the first entry. And then here, for the second entry, -1 times 2 gives me -2, plus 1/2 times 10 gives me 5. And I just have to do the rest of the arithmetic, right? -3 plus 10 gives me 7. 5 minus 2 gives me 3. So this is my unique solution. Right? X sub 1 is 7, x sub 2 is 3. So we can use inverses to solve. Let's find another inverse. Find the inverse of the following matrix. Here we have A with rows 3, 6, 4, 7. So A inverse, I want 1 divided by, multiply on the main diagonal, 3 times 7, and then subtract away, multiply on the off diagonal, 6 times 4. And this is my coefficient, but I'm going to multiply it into, here we got to fix this. On the main diagonal, the 3 and the 7 are going to switch. So 7 upper left, 3 bottom right. The 6 and the 4 stay where they are, but we have to flip their signs. So now it's a -6 and a -4. And let's keep going with this, see what we can get. My coefficient, I have 1 over 21 minus 24. And then just rewriting. We'll say, well, this is really 1 over -3. And now all I have to do is bring this -1/3 in. So the sign is going to flip, and I have to divide everything by 3. So here I'm going to get, well, -7/3. That's the best I can do. Negative divided by negative is positive. 6 over 3 is 2. Negative divided by negative is positive. 4 over 3 doesn't reduce, so that's 4/3. And then 3 divided by -3 is -1. So this is A inverse. It's this matrix with rows -7/3, 2, 4/3, -1. So not so bad to find the inverse of a 2 by 2 matrix. What about, though, if I have a larger matrix? Here I have a 3 by 3. And this is where we're going to go back to that theorem that we had. So let me go back to that theorem and read it again. An n by n matrix A is invertible if and only if that matrix A is row equivalent to the identity matrix, meaning we can row reduce it into that identity matrix. If this is the case, then any sequence of elementary row operations that reduces A to the identity, IN, will also transform In into A inverse. Well, okay, so how should we really interpret that and what can we do? What we need to do for this 3 by 3 matrix, because I can't use my formula for 2 by 2s because I don't have a 2 by 2, is I want to take this matrix A and think of it like augmenting with the identity. In this case, it should be the 3 by 3 identity of the same size. And I want to row reduce so that I get the identity on the left. Now, when I do that, when I row reduce and push the 3 by 3 identity to the left, what I'm going to get on the other side is A inverse. So this is a clever way that we can find the inverse of a 3 by 3 matrix. So I want to start, I'm just going to rewrite A. And then I want to augment this, but not with a column. I'm going to augment with a 3 by 3 matrix. It's going to be the 3 by 3 identity. So with the first row 1, 0, 0, 0, 1, 0, 0, 0, 1. Now my goal is to row reduce, and really I want to focus on the left part of this sort of augment line. And I want to keep track of what happens over here as well, but I want to try to reduce this till I get the identity pushed over to the left. So we'll say, okay, well, let's go ahead and start reducing. So here I can use this 1 in the upper left corner to try to get zeros underneath it. So I can replace row 2 with row 2 plus 4 times row 1. And I can replace row 3 with row 3 plus 2 times row 1. Let me just rewrite row 1. Because I'm not going to do anything to it. And then here in row 2, negative 4 plus 4 times 1 gives me the 0 that I wanted. Negative 7 plus 4 times 2, so negative 7 plus 8 gives me positive 1. 3 plus 4 times negative 1, so 3 minus 4 gives me minus 1. But I have to continue this. So now 0 plus 4 times 1 gives me 4. 1 plus 4 times 0 keeps my 1. And 0 plus 4 times 0 gives me 0. Now in row 3, I'm replacing with row 3 plus 2 times row 1. So I get negative 2 plus 2 times 1 gives me 0. Negative 6 plus 2 times 2, that's negative 6 plus 4, gives me negative 2. And 4 plus 2 times negative 1, that's 4 minus 2, gives me positive 2. And I have to continue over here. 0 plus 2 times 1 gives me 2. 0 plus 2 times 0 gives me 0. And then 1 plus 2 times 0 gives me 1. So this is what I wind up with at this stage, but I want to keep going. I want to keep going with this reduction. So say, what about next? Well, I can do some more row reduction, for example, in row 3, and I can use row 2 to sort of facilitate that. So let me go to row 3 and replace that with row 3 plus 2 times row 2. So I'm going to rewrite row 1. Rewrite row 2. Here in row 3, I get 0 plus 2 times 0 gives me 0. Negative 2 plus 2 times 1 gives me that 0 that I wanted. And then 2 plus 2 times negative 1 gives me another 0. And then if I continue on, I'm going to get 2 plus 2 times 4, so that's 2 plus 8 gives me 10. 0 plus 2 times 1 gives me 2. And 1 plus 2 times 0 gives me 1. But notice right away there's a problem. What I was trying to do is I was trying to get the 3 by 3 identity on this left-hand side. So we wanted this left-hand side to look like that 3 by 3 identity. And then whatever I get on the other side is whatever I get. But notice this bottom row is just a row of all zeros. That's going to mess everything up. I'm not going to be able to get that 3 by 3 identity because I'm missing some pivot. Where is it? It's not there. It's never going to be the identity. I'm not allowed to have any row that looks like this. It's got to be something for me. There's nothing for me here. What is this trying to tell me? What can I do to interpret this? What is this trying to say? This means, and unfortunately this can sometimes happen, this means our matrix A is not invertible. My process to find the inverse was to bring this identity matrix to the left side. It is not possible. Since it's not possible, that means the matrix that we have is not invertible. Another sort of fun fact or a bonus key term, not invertible is the same as saying singular. We have a singular matrix. But so we tried to find the A inverse. We can't find it. Got this extra sheet here for you to write your notes. A inverse does not exist for this matrix A. Is that always the case? No. Matrices sometimes have inverses, sometimes they don't. We're going to talk about the invertible matrix theorem next in the course, where we can really start talking about these ideas a lot more. But for now, just kind of get used to it. Sometimes there's not an inverse. We hope that there is one, not always. Let's take a look at another example of this. I don't want to leave this lecture on a failure. Let's see if we can get an inverse. We'll do the same process. You have a new matrix A, new day, fresh start. You rewrite matrix A, but don't close it off yet, because you know we're going to augment this with the 3x3 identity matrix. Bam, bam, bam. And now I want to row reduce so that I can try to push the 3x3 identity to the left here. All right. Hey, don't wait up. I can use this one in the upper left corner to get zeros underneath it. Row 2 already got the memo. Row 3's got some work to do. So here I can replace row 3 with row 3 minus 5 times row 1. I want 5 minus 5 times 1 to give me that 0. It's the only way to do it. So row 3 minus 5 times row 1. And I can rewrite rows 1 and 2. Get that out of the way. They're staying as they are for right now. But in row 3, 5 minus 5 times 1 gives me 0. 6 minus 5 times 2, that's 6 minus 10, gives me negative 4. 0 minus 5 times 3, 0 minus 15, gives me minus 15. Continue. 0 minus 5 times 1 gives me negative 5. 0 minus 5 times 0 keeps my 0. 1 minus 5 times 0 keeps my 1. Now I want to keep reducing. So now I can look in row 2, and I can use this 1 right in the middle, well, you know, of the left side. I can use this 1 to get a 0 above it and beneath it. That shouldn't be too bad, just the arithmetic. So what am I going to do in row 1? Well, I'm going to replace that. I want 2 minus 2 times 1. I'm going to replace row 1 with row 1 minus 2 times row 2. And what about in row 3? In row 3, I want negative 4 plus 4 times 1. So I have to replace row 3 with row 3 plus 4 times row 2. And I can just rewrite row 2 to get that out of the way, since, what's that little glitch? Get rid of that. You're worth it. So we'll go back, we'll fix it. That is 0, 1, regular looking for, and then continues augmented 0, 1, 0. But let's work in row 1. So 1 minus 2 times 0 is 1. 2 minus 2 times 1 gives me that 0 that I wanted. 3 minus 2 times 4, so that's 3 minus 8, gives me negative 5. And then we continue. 1 minus 2 times 0 gives me 1. 0 minus 2 times 1 gives me negative 2. And 0 minus 2 times 0 gives me 0. Now we're also working in row 3, replacing with row 3 plus 4 times row 2. So 0 plus 4 times 0 gives me 0. Negative 4 plus 4 times 1 gives me that 0 that I wanted. So very good. And negative 15 plus 4 times 4, that's negative 15 plus 16, gives me positive 1. And we continue. Negative 5 plus 4 times 0 gives me negative 5. 0 plus 4 times 1 gives me 4. And 1 plus 4 times 0 is going to give me 1. Now so far it looks good, and it looks like this one's going to have a little bit of a happier sort of end result than what happened just previously. But I want to keep row reducing. Now, columns 1 and 2 look really good. This third column, I can use the 1 in row 3 to try to get zeros above it. You know the drill, row reducing, right? So what do I want? I want negative 5 plus 5, so I'm going to replace row 1 with row 1 plus 5 times row 3. Give myself a little bit extra space there. And in row 2, I want 4 minus 4 times 1, so I got to replace row 2 with row 2 minus 4 times row 3. And I can actually just rewrite row 3 to get that out of the way. 0, 0, 1, and we continue augmented, negative 5, 4, 1. And let's see what we wind up with. So here, working in row 1, replacing with row 1 plus 5 times row 3, we get 1 plus 5 times 0 gives us 1. 0 plus 5 times 0 gives us 0. Negative 5 plus 5 times 1 gives me that 0 that I wanted. But we have to continue. So 1 plus 5 times negative 5, that's 1 plus negative 25 is going to give us negative 24. Negative 2 plus 5 times 4, that's negative 2 plus 20, gives us positive 18. And 0 plus 5 times 1, that's 0 plus 5, gives us 5. Now in row 2, we're replacing with row 2 minus 4 times row 3. So 0 minus 4 times 0 gives us 0. 1 minus 4 times 0 gives us 1. But then here I wanted 4 minus 4 times 1 gives me that 0 that I needed. Looks good. Let's see what continues. 0 minus 4 times negative 5. Be careful with the signs. That's going to be 0 minus negative 20, which is going to give me positive 20. I get 1 minus 4 times 4, so 1 minus 16 gives me negative 15. And then 0 minus 4 times 1, that's 0 minus 4, gives me negative 4. Now notice that I started with matrix A on the left and the 3 by 3 identity on the right. And I went through my row reduction, did my very best. And now the 3 by 3 identity is on the left. Well, what's this on the right? This is A inverse. So now I have the 3 by 3 identity on the left and A inverse is on the right. Right, because I had started with, I'll write it over here, I started with A on the left and the 3 by 3 on the right, and then I was able to reduce, row reduce, to get this. So what I have on that right-hand side is A inverse. So I found the inverse. It does exist for this one, thank goodness. I can just state it now. A inverse has that first row, negative 24, 18, 5. It has a beautiful second row, 20, negative 15, negative 4, and an amazing third row, negative 5, 4, 1. That is our inverse, and that's how we can find it for these. And this will work for a 4 by 4, a 5 by 5. Right? This will work for all of those larger sizes. 2 by 2 we have that nice formula for, so we can just do that. Hey, that's it. I hope you enjoyed this sort of more brief discussion on inverses. We're not done talking about inverses. We're going to keep this discussion going. We got a lot more to talk about next with the invertible matrix theorem. But for now, I just want you to get comfortable with the mechanics. So work on your 2 by 2s, your 3 by 3s, maybe even take a look at a 4 by 4 if you're feeling up to it. But hey, no matter where you are and what you're doing, I want you to remember to always keep learning, keep dreaming, and follow your heart. You know what? I'm not really going anywhere. We're going to do more math soon, so I will see you later. But until then, make sure you take care. I will see you next time.